Today we start composition of functions. So we take two functions, let f and g be two functions. We have two functions here. Then the composition, that is usually denoted by small o, small circle. So we have FOG or GOF or FOF, you may have GOG and so on. These all are called composite functions. Composite functions. Composite functions means combination of two or more functions. Combination, which is also called composition. Composition of two or more functions. Two or more functions. Like this, for example, if I write sine of x square, so this is a combination of two functions. One is sine function, other one is x square, like this. You may have for example tan of sine x. So this is also composition of two functions. One is tan, the other one is sine. You may have like this tan cube x. So this is a combination of two. One is 10 and the other one is x cube, like this. So these are all called composite functions. Now let's see precisely how to define this. So I'll take two functions like this. Let f be a function from a to b. A is domain, b is codomain. You have another function g from b to c, where b is domain and c is codomain. This be two functions. Be two functions here. Now, with the help of these two, as I explained, we define composite function. That is, I'll write GOF. GOF. So here, this B is common, so it will be from A to C. From this to this. We'll come to know why it is from A to C. So what we do, we take one member from the domain of function f, which is a, suppose x. This is in a. Now here, if you look at from right side, the first function is f. So on x, I'm going to apply f. So this is fx. Now you know that this is obviously in codomain. So this is b. Now b is also domain of the other function, that is g. So now on this number, whatever it is, suppose this is 1 and this is suppose 20. Then on this, I'll apply the another function with it, which is g. So on which one you applied g? That is on fx. So it is g of fx, like this. And obviously g is a function from where to where, b to c. So this will be in c. So finally, you have a member x from a to c. So that's why it's the function from a to c. And how you got this? It's application of two functions one by one. You take one member x, you apply f first, so f of x. Then on this you apply g, so it is g of f of x. And this is called g o f at x. This is the definition. For every x in the domain of the function f. Remember here, this function starts from domain of f to codomain of this function. This is the domain of f. And this is codomain of the second function. It is operated from inner side. Look at here. On x, f applied first and then g. this is called composite function. It is nothing application of two functions one by one, first f applied and then g applied. So here if I apply f on x, you are in B, then I'll apply g, so you are in C. So indirectly it's a function from where to where? A to C. So we wrote A to C. And on x you are applying f first, so fx, then you are applying g, so g of fx, and it is sometimes denoted by this symbol g o f at x. This is the definition. On x you apply f first and then g first. This is what it is called composite function, and it's a function from A to C. Remember, from domain of this function to codomain of this function. So this is composite function. You can define same way, for example g o f also, f o g also, sorry. If I want to get f o g at x, then on x you apply g first and then you apply f, so it is f of g of x. So this is f o g function. It is application of two functions one by one. Remember, application of two functions one by one. Here on x f operated first and then g, here on x g operated first and then f. This way we can find composition of two functions. So now let's see some examples. You will realize. Let's take function f from real numbers to real numbers, where fx is, for example, given by sin x, trigonometric function. Another function g from again r to r, and I'll take g of x equals to, let's write for example 4x. The question here, all these four sides are equal, so we find all these functions. Let me find f o g, g o f, composition of f with itself, and g o g, that is composition of g with itself. Let's find these functions. Here we see that this all f o g, g o f o f and g o g, all are functions from real numbers to real numbers. In general, suppose if you are finding f o g, then it is from domain of this to codomain of this, remember. But here all four sets are same here, so it is from R to R. Normally when you find g o g, it will from domain of this to codomain of this. If you find f o f, it is a function from domain of this to codomain of this, but here all are functions from R to R. Now we find the formula for this. So formula, you need variable x. So first one, f o g, we find this. So we start with f o g at x. X is any variable. This is true for every x. So on x, first g is applied. So it's f of g of x. First g and then f. Now you have prepared formula for gx. What's the formula for gx? It is 4 times x. So it is 4x. Here gx is 4x. Now what's the formula? Now outside you have f. Now what is the rule of this function f? If you have x, then it becomes sin x. If I write 0 here, then this is sin 0. If I write here 1, then this is sin 1. If I write 2, then this is sin 2. If I write 100, then this is sin 100. Remember, that's the rule. Now here you have 4x. So if I apply the function, this will be sin 4x. Remember. What happens here, if you observe carefully, that x is here replaced by this inner expression, which is 4x. Don't get confused with this x and 4x. I repeat here again. What is the rule for function f? If inner is x, then here it becomes sin x. Now here instead of x, what I have? 4x. So it will be sine of this bracket, which is 4x. This way it is done. So this is true for every x. This is a new function. This is f o g. This is a new function. It's a composition of two functions. Which two functions? One is sine and the other one is 4x. You already come across such functions earlier, but now this is explicit composition operation. Sine 4x, it's not like this, remember, sine into 4x, this is wrong. Sine of 4x, don't put dot here. Next, GOF. So we start with GOF at x. So it is G bracket of fx. That means on x first f is applied and then g is applied. Now circle is no more because I wrote the bracket. Now write the formula for fx. What's the formula for fx? You know it is sine x. So here sine x. Now on this you are going to apply the function g. Now what is the rule for function g? X become 4x. If I write 1 then 4 into 1. If I write 2 then 4 into 2. If I write 3 then 4 into 3. If I write 7 then 4 into 7. If I write 100 then 4 into 100. So here what I'll get? 4 times sine x. I repeat, what is the rule for function g? If you have x then it becomes 4 times this bracket, 4x. Now here instead of x what I have? Sine x. And I'm applying g, so it is 4 times. Instead of this x you will get the sine x here. I hope this is clear to you. So this is a new function, GOF at x. One more time I'll explain. In the formula of the function g, x is replaced by this bracket. I repeat, in the formula of the function g, that x is replaced by this sine x. So 4 times sine x, remember, I repeat, this x is replaced by this sine x, so 4 times sine x. So this is a new composition of function. This is a new function, 4 times sine x. This was sine 4x. Let us go for now f of f. So one by one, same function. So f of fx, application of same function twice. Now what is fx? It is sine x. Fx is nothing but here sine x. Now again f. Now what is f? Here look at f. F is nothing but the sine of this number. Now here inner number is itself sine. So what we'll get? I just again emphasize on this. If I have x, then it becomes sine of this number, which is x. Now this number is sine x itself. So what I'll get here? If I apply the same function, instead of these you apply sine. So here in front of this again you apply sine. So sine of sine x. So rule for function f says that instead of x you write sine x here. So I'll write sine of sine x. This is composition of f with itself twice. Sine of sine x, remember. Such things you already come across in inverse trig functions. Sine of sine x. I repeat one more time here. If I want to get this, then in the formula of the function f, that x is placed by this sine x. So this x is placed by this sine. So sine of, instead of x you are going to write this bracket, which is sine x. So you have this. And similarly, if I go for GOG, that is GOG at x, that is g of gx. So first formula for g. What's the formula for g here? It is 4x. Now again same function. Now what is this function? Inner number into 4. If I write 100 here, then 4 into 100. If I write 20 here, then 4 into 20. If I write 3 here, then 4 into 3. Now here what you have? You have 4x. So what will get? 4 into that inner number, which is 4x. So this becomes 16x. There is a new function which is called GOG. Now we still state two important results about this composition. The first one is, if I find FOG and if I find GOF, these two need not be equal every time. That means what I'm trying to tell you is composition is not commutative. Not commutative if you remember matrices. In matrices you had the same thing. A into B need not be same as B into A. And the second one, if I go for three functions, if I find F, O, G, O, H for three functions, and if I find F, O, G, O, H, so I've just change the bracket. You see, this is FOG, this is GO. These two are always equal for any three functions. So here we say that is this composition is associative. So it is exactly same as matrix multiplication. Matrix multiplication is associative but non-commutative. Same way this composition is not commutative but it is associative. These two are always equal. FOG in general need not be same as GOF. One more thing, if you remember identity function. If function is composed with identity function, where I stands for, if you remember identity function 11th standard, identity function. So if function f composed with identity, reverse way, if I do IOF, then your answer will be f again, where f is any function. So this result says that a function composed with identity function gives you that function itself. This is again same as matrices result. If you remember, A into identity matrix equals to identity matrix into A equals to A. This is always true. So these are the three standard results about this composition operation. Composition is non-commutative like matrices. For three functions, if you do composition in this way, this is always associative like matrix multiplication. And function composed with identity function is always the function itself. So this is about identity function. This is always true. Now, before I get into next point, I'll take two functions here. Let me, for example, here, function f here. Let's take R to R, function f from R to R, fx equals to, I'll take, let's write 2x plus 1. Another function, again R to R, and I'll write in this way, gx equals to x minus 1 by 2. These are the given two functions. We find all four sets are equal. So we find FOG and GOF. This is the question. We want FOG and GOF. So clearly you can see that FOG would be a function from R to R, and GOF is also a function from R to R. These are the two functions. These four sets are equal. Now let me see this. In this, now you know, first G is applied, then F. In this, first F is applied, then G. So I'll find FOG at any x. So it would be f of g of x. So it will be f of, now formula for g. What's the formula for g? That is this one. That is x minus 1 by 2. Now on this you are going to apply f. Now what is the formula for f? That is this number into 2 plus 1. So I'm using function f. Or in another language, in the formula of the function, x is replaced by this entire bracket, because here inside the bracket you have this, here inside the bracket you have x. So in the formula of f, x is replaced by this much, so I'm replacing x there. So 2 into x is replaced by this inner expression, x minus 1 by 2 plus 1. 2 will get cancelled, 1 will get cancelled, so we'll get just I. And you recall, if FOG at x, if you are getting same for every x, then this is called identity function. So FOG equals to I. It's a function from R to R, if you remember. So it is called identity on R. IR we usually write. It's a function from R to R. Same way, let me see this. G of f at x. So first f is applied on this. So g of fx on x, first f is applied. Now write the formula for f. What's the formula for f? That is 2x plus 1. Now on this fx is replaced by this. Now on this you have 2x plus 1. Now formula for g. Now what is the rule for function g? This number minus 1 by 2, or in another language, in the formula of g, in place of x you write this bracket. I repeat, in the formula of g, instead of x you copy this bracket. So I'm repeating again, in the formula of g, instead of x you write this bracket. So I'm writing that. Instead of x I'm writing this. So 2x plus 1 minus 1 is already there, remember, by 2 is also there. What I did, just in place of x I have placed this bracket. Now you simplify, 1 will get cancelled, 2 will get cancelled. This is x. So here you had started with any x and you are getting x again. So image of every element is itself. So such a function is called identity function. So this is I, R to R. So we write usually IR. So here FOG and GOF, both if I composed, you will get identity function. Now you recall matrices. If I recall matrices, if you remember, in a matrices, if I recall this, for given matrix A, if there is a matrix B, if equals to In, and reverse, B into A is also In, then this B is called inverse of A, if you remember, and we used to write this. So here same way, here this function G, here G is called inverse of F. G is called inverse of F, and we write by this symbol. We write G equals to F raised to minus 1. This is the symbol. This does not mean 1 upon F, remember. This does not mean 1 upon F. So this is a concept of inverse function. We did in inverse trig function, if you remember. Even in matrices also we did same concept, but now this is for function. So when one function is said to be inverse of the other function, if their composition GOF and FOG both should be identity function, then this is called inverse of this, and we write raised to minus 1 symbol. And in this case we say that F is invertible function. Invertible function means it has an inverse. Same concept of what we did in case of matrices. If you remember, one matrix into other matrix equals to identity. So here same way, instead of multiplication you have composition. Composition of FOG and GOF is identity. Then the G is called inverse of F, and we write this symbol by raised to minus 1. And here in this case F is called inverse of a function. You recall even inverse trigo. Now you can answer. If you remember, sine inverse of sine x. So what you are getting, x. This is just identity. You recall tan inverse of tan x. So of means this is composition, so you are getting same. That means this is inverse of this function, this is inverse of this function. So inverse of tan, we used to write tan inverse. That means if I compose these two, you were getting same, if you remember. So here that was just for trig functions. Now this is for any function. Invertible function, or it's also called inverse of a function. So we start with a function. Let f be a function from a to b. Let f be a function from a to b. Now if there exists a function, let me call g. Now you know inverse trig. It is now from b to a. Domain and codomain get interchanged such that if I find f of g, or even if I find f of g, and if I find g of f, if I find these two functions, so in f of g, which function applied first? G. So it starts from here, domain of g to codomain of f, so it's from b to b. So this should be identity from b to b, so IB. IB stands for identity from b to b. Now go to this. So it starts from domain of f to codomain of this g, that is from a to a. So this is IA. Why IA? I repeat. I stands for identity. IA means it would be identity function from a to a. So here, as per definition, it starts from here, domain of f to codomain of g. So this to this. It starts from g, domain of this to codomain of this, so IB. So if we have these two conditions, then g is called inverse of f. And we write by this, we write g equals to f raised to minus 1. So therefore f inverse will be a function from b to a, where f was a function from a to b, and f inverse will be identity on b, and f inverse of it's again identity on a. So this is always true for function and its inverse. If you remember, matrices, inverse of a matrix into a equals to identity matrix in. A into a inverse equals to in. But here operation was multiplication, here operation is composition, o, small o. So even if you recall inverse trig functions, you know sine inverse function from, for example, close interval minus pi by 2 to close interval minus 1 to 1. Inverse was in the reverse way. So this is the definition. When two functions are said to be inverse of one another, if their composition equals to identity. I repeat, when two functions are said to be inverse of one another, if their composition f of g and g of f both are identity functions. So f of f inverse and f inverse of f, if both are identity functions, then this is known as inverse of this. Remember here, you know it one more time. Here f inverse is equals to 1 upon f. This is not true, remember. F inverse does not mean 1 upon f, you know it. Even sine inverse x is also not equals to 1 upon sine x, you know it. This is especially for sine inverse. Here it's for in general any function. Okay, so in that previous example, their fx was this 2x plus 1, and you had that function g, so that g was indirectly, that gx was this x minus 1 by 2. So indirectly this is nothing but the inverse of f, so it is x minus 1 by 2, because there we had shown that f of g and g of f both were identity functions if you see the previous example. So that g was indirectly inverse of f, and it is therefore this. So this is a concept of inverse function. It's not difficult for you now because you studied in matrices as well as inverse trigo functions. So now we note down some results about inverse. The first part is, first result is f inverse exists if and only if, you know, I did in the beginning of inverse trigo function, f is bijective. Now recall what is bijective. That means f is 1 1 as well as onto. Such a function is called bijective. So that's why if you go back to beginning of inverse trigo functions, I had explained this concept. Every function may not have inverse. Inverse of f exists if it is bijective. That means it has to be 1 1 and onto. You remember matrices. Inverse of matrix need not exist. It exists only when its determinant is non-zero. That was condition. So whenever you find the inverse of a function, first you need to see that it is 1 1 and onto or not. If it is both 1 1 as well as onto, then such a function is called bijective, and hence you can find the inverse of a function. So we say that here f is invertible. Invertible function. Invertible means inverse exists. That's one. Second, every time inverse may not exist, but whenever f inverse exists, then it is unique. Then it is unique. Unique means exactly one. Function cannot have two different inverses if it does exist. It may not exist. You know what condition you required. But if inverse exists, then it is unique. Third one, if I find inverse of a function twice, then you will get the function itself. This is always true. Fourth one, you had the same condition for matrices also. If I find f o g, the whole inverse, you did such things in matrices also. A into b, the whole inverse equals to b inverse into a inverse. Their operation was multiplication, here composition. So find f o g first, then inverse. So it would be g inverse o f inverse. Order get reversed. For any number of functions this is true. f o g, the whole inverse equals to g inverse o f inverse. This is very important result. For any two functions this is always true. First one, this is a condition. F is invertible, that is inverse exists if and only if it should be bijective, 1 1 and onto. So whenever you find whether function has an inverse, you check whether it is 1 1 and onto or not. Inverse is always unique if it exists. If you find inverse of function twice, you will get the function itself. And f o g, the whole inverse, gives you g inverse o f inverse. This is always true for any two functions, remember. Now one more thing, this is, you can consider as a result. If you have function from R to R, linear function, if I take in general ax plus b, where a should not be 0, non-zero. This is a linear function, you know, now we did this. Linear function from R to R, then it is always 1 1 and onto. F is 1 1 and onto. Right. Prove it, we did it, you should know now. Why? Try for this, you should know. F is 1 1, we did it number of times in earlier section, and it is onto also. Every linear function from R to R is always 1 1 and onto. Try to prove this, y 1 1, y onto. In MCQs you can use this. So here f inverse, from where to where? R to R again. F inverse from R to R exists because it's 1, 1 and on 2. Now question is, what's the formula for F inverse? So F inverse X equals to, this way you can find the formula. Take function as Y. So what is Fx here? Ax plus b equals to y, and get x as a subject of expression. So it will be y minus b by x. If you remember onto part, proof of onto part, by a, x equals to y minus b by a. This is x. Now just in place of y you put x, so x minus b by a. This is the formula for inverse, for linear function. You can verify, you try, you compose these and this, you will get identity. This is just for your information. Verify, if you try, verify that if you compose these and this, f of inverse, you will get IR, identity, and f inverse of f, again you will get IR. So this will be now inverse of f. For any linear function, like if I have, for example, 4x plus 3, then its inverse will be, directly you can write, take 3 on the other side, so x minus 3 by 4. One more, if I take, suppose I have gx equals to, let me write 2x, let me put, for example, 7. So inverse of g will be, you imagine there is x on the other side, so x minus 7 by 2. So this way, if it is a linear function, and remember from R to R, then inverse you can write directly like this for linear functions. And we already noted earlier that every linear function from R to R is bijective. So this is applicable only for linear functions, provided that it is 1, 1 and on 2.